All right, so in section 1.5, what we're studying are proofs that are not valid. The opening exercise is for you to explore this statement. So again, the statement says, consider the following statement. There are 3 errors in this sentence. Is this statement valid?
No.
Yes, no, why not? Let's hear from some of the groups. Yep.
There's 2 errors within the third error. It's
So there's 2 errors that you see in there. So which ones are you seeing?
3 and errors.
Okay, the spelling of the word 3 and the spelling of the word errors. Okay? But you said you think there actually is a 3rd error in there.
Yeah.
So what is that 3rd error?
It's that there aren't.
Okay, so the 3rd error you're saying is the actual sentence itself as a whole. You're saying that sentence stating that there are 3 errors in the sentence is actually another error. So that makes this statement valid. Okay, did anyone have a different look at that? Did anyone say this is totally not valid? For any reason, yeah. Okay, there's only 2 errors in the sentence. The word 3 and the word errors. Okay, so you don't agree with that group over there that there's a 3rd error. The sentence itself is an error. Okay, all right. Anybody else have a different thought on it? All right. There is no right or wrong answer here. I mean, I think an argument could be made for both. It seems to be valid that there are only 2 spelling errors in the sentence. Now, if you're considering the sentence statement as a whole being considered as one of the possible errors, then you could say that, yes, this is valid because there are 3 errors, 2 spelling errors and 1 meaning error. But if you're just saying, you know what, within that sentence, within the spelling of the words of that sentence, there are only 2 errors, this is not valid. This is the kind of thinking that I want you to be engaged in this chapter, or in this section, I should say. Okay, so that's good. Is the statement valid? It's open. It's open to argument. I like both arguments. Is there a 3rd argument or not? All the other groups know they've kind of settled on one of those 2. Okay, all right. So let's take a look at another example from the text. This one right here. Okay, so this is investigate the math. Mo was working with tiles on grid paper. He used right triangles and right trapezoids. And this is what he did. He cut these things out or whatever. He drew them. And if you arrange the tiles this way, there's an area of 65 units. So if you count all the squares that are inside this collection, there's 65. But if you rearrange them, he said, look if I rearrange them a different way, now it only covers 64 squares. So since he used the exact same tiles, he said, this is a proof that 64 actually equals 65. So why don't you take another 1 minute and talk with someone next to you about what is up with this. Does 64 actually equal 65? Or where may there be some invalidity here? Okay, so go ahead and take a moment to discuss that. Okay, so what are your thoughts?
So one time I saw this thing where someone had a chocolate bar and they rearranged it, and so then they had like 1 extra piece. So I was thinking maybe with this, like it's still the same amount, but it's like rearranged differently, so it's less. Gives less surface area.
Okay, so it's the same. You think it's the same amount? So you look at these. Do these shapes appear to be the same dimensions? I mean, did you count all the squares and they're actually the same dimensions? Okay, I think I did this before and they are exactly the same. Okay, so you're saying you saw something once where you did chocolate bar, you cut them up, you rearrange, and all of a sudden it seems like you have an extra piece. I guess it's grid paper. The grid paper is consistent. So if you count the actual squares here, it appears that 64 versus 65. So somehow, okay, so that's not a real reason for why this might have happened, but okay, I'm following you. Anybody else have another thought? A reason? What could account for this discrepancy? Coleman?
I was kind of thinking of the same logic applies to like a piece of paper. Like it covers more surface area like this, but I could fold it up and it could be like this small. But it's still the same on the paper. Okay,
that's okay. So let's think about that. If you take a piece of paper, a big piece of paper, and you fold it up as many times as you can, and all of a sudden it looks like this small piece of paper, it's still the same total surface area, but not, okay, that's good. We're not actually folding anything up here, so I like that thinking. That's good thinking. But something else is wrong here. One more chance at it, anybody else? This is a tricky one, I would agree. Now, what if we had time? If we had time, what we'd do is I'd get you all to draw this. It would take the whole class, so I don't want to spend the whole class on this. But if you actually had a grid paper and you actually cut out each of these shapes and tried to line them up, you would notice something. And that something would be right around here, this middle line right here. In this one right here, I guess, in parts of this, there would be slight overlap of the pieces. And in this one, there would be a gap, a big gap right here. Now, the reason why this appears to be really strange is because of the thickness of the lines in between. So if you got rid of the black kind of borders from each shape, you would actually see that there would be a little bit of a gap, and this tiniest little gap, but from this corner all the way to this corner, it's a gap, and it actually would add up to one full square extra. So that's the tricky part of this one. And I was like, well, that's not really fair, Mr. Maxwell, but well, it sort of isn't. But if you actually were to cut these shapes out or to do that sort of thing, you would see that you wouldn't be able to line them up just properly. It would sort of like they would kind of meet at the corners, but there would be a little bit of a gap, bigger gap, and then it would kind of come back to the middle. Just a slight amount. So that's what's happening here. It's a bit of trickery. Well, sort of trickery, I guess. So let's move on. And they say construct and cut out, and you can actually see that for yourself. But moving on. Okay, what are we going to do here? Let's move on to this one right here. Okay. This is an algebraic proof, okay, which again, judging from last section there with that one question, I'm still wondering how many of you have a real handle on algebraic proofs. It takes a little bit of time. So I want to do this example. And Bev here, she seems pretty clever. He, okay, sorry, it's a he. I know Bevs that are she's, so Bev, he, okay. What could that be short for? Bev? Is there like a Beethoven? Oh, maybe. Beethoven? Yeah. I would have said Betty for Beethoven. Anyways, Bev, maybe. I know. Well, I'm saying Bev and Betty are both seeming to me... Okay, forget it. Well, that's what I'm saying. This is what's tricky about that. I don't know any boys named Bev. Do you know any boys named Bev?
My future son.
Your future son. You're going to name your son Bev. Okay, I will hold you to that. I will hold you to that. I don't believe it. So someday you need to come and prove this to me. Okay. Wholly off track, Batman. Okay. Snap back here. So Bev, apparently male, can prove that 3 equals 4. Let's take a look at Bev's proof. This is on page 37. Follow along up here or in your textbooks, please. Suppose that, okay, everybody watching? Suppose that A plus B equals C. So this is his starting sort of assumption, all right? This statement can be written as, so what's happening here? A could be written as 4A minus 3A. See that? That little chunk right there represents A. This little chunk right here, 4B minus 3B, represents 1B. And then over here, 4C minus 3C represents 1C. So building error, that's very clever. I think that's quite clever. So what else can we do? Can we rearrange things? Look at that. The 4s, the terms with 4 in it, they rearranged. 4A plus 4B, and then minus 4C here. And then they put the other ones on the other side. And then they factored a 4 out. He, Bev, factored a 4 out, both sides. And it appears that there is a common A plus B minus C. That's a factor of both sides of the equation. And so he simply divided that common factor from both sides of the equation and ended up with 4 equals 3. So can anyone tell me what went wrong? Because this is not a valid proof. 4 does not equal 3. There is something that happened inside this proof. It's tricky to see. It's kind of hidden. But what happened inside this proof that went wrong in the proof? Bev did something that you can't mathematically do. So ideas, yeah, you up first? It's minus 4C, like right here? Yeah, that's right. The 4C comes over to the other side as a negative. So this is still true, though. That's 4 times the negative C would be negative 4C. So that's not the problem. Good guess, though. Another one? Yeah. Okay. Okay. Yes, that is absolutely correct. Very good. So let's just go over that, what was said there. So A plus B, if that is the same as C, okay, so let's just pick a number example, like A plus B, let's say that's 7, and C is 7. Well, if you move C to this other side, you would have 7 minus 7. That would be equal to 0. So A plus B minus C actually equals 0. And check out what Bev did down here. In the last step there, he divided both sides by 0, which is an invalid algebraic step. You can't do that. You cannot divide by 0. You can't take something and divide it into 0 groups, because you basically are saying, I have a collection of something and I need to make this disappear. That's not a valid way of dividing things. Okay, so you can't divide by 0. All right, good catch. Does everyone see that?
Yep.
Okay, so I'm going to clip this over, and let's copy this down into your notes. Just take 10 or 15 seconds and copy this down right here into your notes. What is an invalid proof? An invalid proof is a proof that contains an error in reasoning, or that contains invalid assumptions. So we just saw the error in reasoning there. It was cleverly hidden, but you cannot in an algebraic proof divide by 0. So that's the big thing. You got to watch for that, okay? That happens a lot in these algebraic proofs that some seem strange with, okay? Or if there's an original or some assumption that's used in that is in error or invalid, that also will affect your proof, okay? So a proof that contains an error in reasoning or that contains invalid assumptions. When we talk about these invalid assumptions, we're talking about an invalid premise. That's another word for something, a statement that is assumed to be true. So it's basically your starting point for your argument, okay? So if we start with an argument, and I am assuming that all of us in here are living people, therefore I'm going to make an argument that you all can respire, or there's some bodily process that you are all doing right now it's because I'm assuming that you're all living, even though some of you maybe look like you're sleeping, think you're living. Okay, good. Everyone's waking. All right. So that would be a premise, right? We start with a basic premise, and basic premise is something you hear. Okay. So this is Prue's solution here, and this is the explanation of dividing by 0, which is not good. Okay. So on page 40, no, what page is this? This is 39 in your textbook here. Liz claims that she has proved, as example 3, that -5 equals 5. So what did Liz start off with? Her basic premise, she assumed that, for this case, she said, okay, let's just say that -5 equals 5, and I'm going to show you how I'm going to prove that -5 must be correct. And so Liz does this. She starts off with a basic premise of -5 equals +5. She squared both sides to show that the square of those two equal values are also equal. And since 25 equals 25, she has proven that -5 equals +5. Okay? So there's something wrong with this proof, right? And if you haven't already seen that, it's the basic assumption or the premise that she started with is invalid. And this is a part of sort of a philosophical argument, kind of a fallacy it's called circular reasoning. Okay, so you know what circular reasoning is. It's maybe tough to define. We have it defined right here. You can jot that down into your notes as well. Remember, I've said for this class here that you'll have an open book quiz coming up, so you might want to have these in your book so that you can check back to them if you need to. An argument that is incorrect because it makes use of the conclusion to be proved. I don't know if you've ever heard this, but this is an example. Circular reasoning works because circular reasoning always works. Right? So that sounds silly, but circular reasoning works because circular reasoning always works. I mean, it always works, so that's why I'm using it. Well, why are you using it? It's because it's true. Why is it true? Well, it's been true the whole time. It's always true, so it's true. But how can you prove it's true? Yes, I can prove it's true because it's always been true. And that doesn't make sense. If you're making some sort of argument, you can't use the conclusion as proof of your argument. Any questions on that? All right, so let's take a look at one more example. This is example 4 in your textbook. And it says this. Here's a number trick, and this is the proof for the number trick, but I want you to take a careful look. Okay? Find the error in this. Okay? So Jose says, if you choose any number, you let the number be n. You add 3, you get n plus 3. You double that, you get 2n plus 6. You add 4, you get 2n plus 10. You divide by 2, you get 2n plus 5. And you take away the number you started with, n, and you are left with 5. So his number trick is going to start off with any number, and it's going to end up with 5. Okay? So first of all, let's just see if that works. So pick a number like, let's pick 3. Add 3, that's going to be 6. Double it, that's going to be 12. Add 4, that's 16. Divide by 2, that's 8. Take away the original number, 3, that's 5. Cool. It works. So what happened? What's wrong? Is that a coincidence, or did you see something?
In his proof, he did n plus 5 instead of n minus 5.
So take away the number you started with. Okay, if you have n plus 5 though, and then you take away the number you started with, you get 5 back. So you get a positive 5. Okay, so I want all of you right now just to pick another number. Okay, you might have the answer, but let's just do this real quick. Pick another number and see if it works for you. Pick another number, see if it works. Let me know if there's a number that doesn't work. You're doing the same thing that I just did. You're picking another number other than 3, and you're doing this number trick, follow the steps. So you're saying that every number you tried worked. What is the problem with this proof then? Is there a problem? Maybe there isn't.
According to the textbook, yes. Yeah.
The textbook is the problem. Okay, do you see? Okay, so watch this. Watch this. The words. Okay, you can do this. You can try it with. And we tried it with a number of different. Nobody found one that didn't work. For real? You all tried this? What's the problem over here, guys? What's the problem over here? There's something that's an issue over here. Terrace, you had your hand up earlier. Okay, so watch this. This person added 4 to get this, and then divided by 2. Okay, so this divided by 2, 2n plus 10, right? Divide by 2 should be 1n plus 5.
So he just went right to n plus 5.
So yes, basically there's an extra step in here that didn't. Yeah. This step right here, from here to here, is invalid. Right? This is not true. So, plus 3, choose a number, add 3, you get this. Double it, you get this. Add 4, you get this. Divide by 2, you get this. You don't get this. Take away the number, and then you should have your answer. So this step does not belong in there. Everyone see that? 2n plus 10, when you divide that by 2, you have to divide all the terms by 2. So this step should not be in there. The number trick is valid, but the proof is not, okay? All right, back to the textbook here. Let's quickly take a look at the summary. A single error in reasoning will break down the logical argument of a deductive proof. This will result in an invalid conclusion or a conclusion that is not supported by the proof. Division by 0 always creates an error in the proof, leading to an invalid conclusion. Circular reasoning must also be avoided. Careful not to assume the result that follows what you're trying to prove. The reason you are writing a proof is so that others can read and understand it. After you write a proof, have someone else who has not seen your proof read it. If this person gets confused, your proof may need to be clarified. So there's some good tips and hints and a review of what we've learned here today in 1.5. Questions? Yeah, keep working. Won't bother you. Unless you're allergic to wasps. Who's allergic to wasps? Yeah, great. Nobody. Good. Keep working.
You might want to kill off